Hello, my name is Evert-Jan Sneekes. I'm with Thermo Fisher Scientific. I'm a strategic marketing manager, and today I'm going to talk to you about the Vanquish system. The title of my presentation, as you can see here, is Revolutionize Your UHPLC Experience. But if I would have to choose a subtitle for this presentation, I would choose Uncompromising UHPLC. And hopefully in the next about half hour, I'll show you some examples what we mean with Uncompromising UHPLC. Well, the Vanquish is a brand new system. It was redesigned from scratch, right? It's not an evolutionary step we wanted to make. We wanted to start with a new platform. And why was that? When we talked to our customers, we heard you say a whole list of feedback of things you want. But if you look through this list, you see more, easier, more, new and better. Right? And the only way we felt we could address these needs that you expressed here was making a brand new system and not change something we already had. And when we look at Vanquish, when we look at our target customers, we distinguish three different groups. So on the top right corner, you have the chromatography power perspective. These are the people that want to get everything out of their separation. They have a sample, they have two peaks, and they will optimize and tune their method and want to play with all the parameters they have in order to get these two peaks separated. So in the top left corner, you have the mass spectrometry perspective. These are people who have a mass spectrometer that needs to work seamlessly with their LC system. And what they want is in the basis a separation that doesn't require further optimization, and any, let's say, co-eluding peaks can be resolved by the mass spectrometer. It's a throughput aspect that they have, it's a data-driven aspect, and they use the power and they harness the power of both their LC and their MS system. And on the top you see there the software perspective. These are the people who are looking for answers. These are the people who want to use these tools to find it. They don't want to tune too much. They just want to run large sample sets, and they just want to have the samples and their answers coming out of their systems as easily as possible. If you then look at the three categories in which we can define the features that the Vanquish system is offering, we see here performance, throughput, and interaction. And each of these categories ties more strongly to one of the categories, but all of these are important for all. So the performance is clearly in the chrome power perspective. The throughput, as I mentioned, is for the mass spectrometry perspective. And the interaction and the ease of use is for the people who are looking for the answers, the software perspective. But what we know for all of these people is that their breakthrough starts with a challenge. And we want that challenge to be your science and not your instrument. And with that philosophy in mind, we developed the Vanquish UHPLC system. So what does it offer? It offers three categories or four categories where we differentiate it in. It's the power perspective, and that's to drive the separation. This is essentially about the pump. And the pump has an extreme high pressure, but the pump offers this pressure over the full flow range. And remember that opening where I said uncompromising UHPLC, we don't want to force you into a trade-off. What we want is we want you to have the benefits of everything. And that means that we give you pressure and we give you a high flow rate, and we don't say you have to choose either or. You can have both on this system. We offer you 2x3 solvents, so it's a binary system. The binary system will use a binary gradient, but by offering 2x3 solvents, you have up to 9 solvent combinations. And this will help you in method development and in method transfer situations. Then we have the accuracy. Right? The accuracy is all about the autosampler. The autosampler needs to have unsurpassed sample dosage to make sure that you can dispense accurately and take up into your loop accurately the amount of sample you want to inject. And to make sure you can do this without interruptions, we have a sample extension in the name of the charger module that allows you to have up to 23 well plates and up to 8,832 samples into your system. And we have automated workflows of barcode reading. If you have so many sample trays, if you have so many well plates, you want to make sure that the system knows where these trays are. So there's barcode readers built in both the charger and the autosampler unit. If you look at sensitivity, this is the detection part. Right? I can separate, I can introduce my sample, but I need to make sure that I detect my sample in the end. So what we have here is we have a VDAD, so a Vanquish diode array detector, which has a very high linearity, but at the same time has noise levels down to 3 micro absorbance units. And this allows you to have both sensitivity and linearity in the same analysis. So you can quantify your main component and identify impurities whether they're present in the same run. Again, uncompromising. It's not one or the other, you can have both in the same run. The Vanquish diode array detector uses a light pipe technology, and what we have introduced at Pittcon this year is a charged aerosol detector as a second detection option, which can even be used together with the Vanquish system. So the charged aerosol detector is a detector ideally for compounds which have no chromophores, and if you use them combinedly, you can pick up and quantify on the best signal that you obtain, and you will find both the compounds which have chromophores and are active, and you'll see them in the diode array, as well as the compounds that will have no chromophores. You will see those on the charged aerosol detector. And the last topic you see here is the confidence, right? To control the separation with the utmost confidence. And for that is the temperature control. Everybody knows that temperature is such a complex factor in chromatography, but also such an important factor in chromatography that we didn't want to compromise here. So we have two thermostatic modes. We have a temperature range which is 5 to 120 degrees, and we have active preheating. And the active preheating allows you to make sure that you have the best temperature going in with the minimal dispersion on it. And then these are looking at individual modules. If you look here at the entire Vanquish system, we have a concept which we call integrated modularity. And the integrated modularity is when you look at the design of the system, where the system is still modular, but it looks like it's one integrated system. But it also goes beyond that, beyond the design aspect. If you, for instance, look at certain features that we have, certain features in a certain module can benefit the results and the performance of another. And let me give you one example here. That's the low baseline noise that we'll have, and I'll show you the data in one of the following slides. The low pump ripple and that we have ensures that we have a stable flow. And that stable flow will mean that you have less noise in your detector. So a pump feature will have less noise in the detector and means you can detect at lower sensitivities. And again, that's also integration that we've built in. Certain features in certain modules will assist the performance of another or the overall outcome of your experiment. What you see here is a whole list of features. The top three are the ones I want to single out here. So the integrated modularity I've just mentioned. We have Viper-based tool-free fluidics. Right? We don't want to make it hard to handle a system which is state-of-the-art and gives you these performance levels. So we have Viper throughout our system, which means you can set up your system completely tool-free. You can change columns, you can change connections just by having finger-tight connections. The third one I want to mention is the biocompatible iron-free flow path that we have. When people do analysis of biopharma, biomolecules, or in biopharma, or in any other area where the complexity of molecules only increases, you want to make sure that your system doesn't harm the sample integrity that you have. And therefore we chose that the Vanquish system should be a biocompatible system by default to make sure that you don't have to choose, there's no compromise here, you will get biocompatibility at the high performance levels that we have. And the Vanquish system is hardware. Essentially what I've talked about so far are 4 modules working together as one system, but that's not the solution you use in your lab. That's not the entire workflow. You'll need a column in every system to perform a chromatographic separation. You will need software to control your system. If you need more throughput, we have the charger module, which is the rack loader. And we have integration with our mass spectrometers in case you need to have that advanced detection behind it. And we made sure that while designing Vanquish and while working on the applications and the solutions we have, we take that integration, what you do in your lab, as the basis for making all these solutions. What I want to show now for the next 5 slides are some highlights that we have on the different modules that we have. So if you look at the Vanquish pump itself, I briefly mentioned the pressure. It's an important feature, but it's by no means the only feature and the only benefit and the only value that a Vanquish system offers. But we have an extreme in pressure. We have a unmatched retention time performance. And I guess that's the most important thing. If you do science, you want to make sure that you can verify your results. And to be able to verify your results with confidence, you need to be able to repeat your instruments. And what you see is the example chromatogram on the bottom. And note these are very small letters that are at the peak, but what it says is that these are 69 overlaid chromatograms and they have a 14 millisecond standard deviation. That means that within this window of 14 milliseconds, we have all of these peaks lined up. So these close to 70 runs. Right? And that's just phenomenal performance. That will give you the capabilities to verify the results. We have an ultra-low gradient delay volume. We have, as I mentioned, the 2x3 solvent channels, and we even taken the Viper finger-tight concept to the check valves of the pump. That if you need to perform some routine maintenance on the pump, you don't need tools. It's still the same tool-free benefits, the ease of use that you can apply here. What we have in the auto sampler is we have a proprietary switching valve. And the idea behind this is we push performance levels the way we've done so far, We want to make sure that the whole rest of the system can handle these performance levels and can provide you with the robustness you need to perform these analyses. And one of the critical elements in any HPLC system is an injection valve. That's the bridge essentially between the atmospheric pressure where your sample is at before the injection and the high pressure at which you do your separation. And the valve that we have, we designed it from scratch to make sure that it gives you the performance, that it gives you the reliability, and gives you also the robustness to be able to enjoy the performance levels a Vanquish system offers for all the runs that you want to do. We have biocompatible fluidics, as I mentioned, in the system, and that includes the autosampler, of course. And we have a new air-to-air cooling concept. And that air-to-air cooling concept goes from 4 to 40 degrees, and that will give you more efficient, more uniform cooling. And the adjustable gradient delay volume, let be the last one I touch upon on the split sampler. That's a very nice feature inside the autosampler in case of method transfer situations. What it means is we have an element in there with a variable volume from 0 to 100 microliters that you can do to hardware-wise change the gradient delay volume of your system. Let's say you want to do method transfer, and the gradient delay volume of the system from which you take your method to the system you want to port it to a Vanquish system is different. Then you could delay your gradient, but if you're not in a position to change the method, which is not the most elegant method to do it, we have a feature built in that allows you to set an idle volume and physically change the gradient delay volume in your system, which we think is the most elegant way of doing a method transfer and mimicking another system's capabilities. If you want to enjoy high throughput analysis, very fast runtimes and prolonged operation, you of course need also the sample capacity. Well, by default the system has 4 well plates that can be in there, which gives you the sample capacity that works in most of the cases. But if you have a high throughput separation and you need that extreme or that higher sample capacity, we have a charger module, which is an add-on, and that allows you to have up to 9,000 sample capacity. It has the integrated barcode reader to make sure you'll be able to find back all the samples that you can trace what is happening in your system. And also the charger module has a temperature control concept, so to make sure that if you have pressure samples that are temperature labile, that these samples are preserved the best way we can. The column compartment that we have in Vanquish has a deactive preheater in there, has an extended temperature range from 5 to 120 degrees, and has these 2 thermostatic modes. What I said is that method transfer is important, and with method transfer the gradient delay volume is an aspect, but the other thing is how you control the temperature. And on certain legacy systems, on most systems actually, there's only one temperature control mode, which is either a still air mode or is what we call a forced air mode. But the way you apply the temperature to your column is the temperature control has a very strong influence on the retention and on the performance you'll get. I have a dedicated slide on that later on. And what we offer is decided to offer both temperature control modes into our system to make sure that you will be able to get recreate the best conditions either for your separation or the best conditions for method transfer. Again, it's not a compromise we want to offer here. We want to give you the best capabilities to do the research you want to do. And lastly, we have here the Vanquish diode array detector. As I said, it uses light pipe technology, has extremely low baseline noise, and has also a very high linear range. And that allows you, and that's the example you see there on the bottom, to do the active pharmaceutical ingredient quantitation and the impurity profiling all in a single run. I like this slide because it shows a lot of the examples and a lot of the performance that a Vanquish system has in one single picture. So what we have is we have a separation capability, which is here expressed in terms of peak capacity. We have a very high peak capacity for traditional Chinese medicine sample separation that we applied here. And so we have very good separation. That's indicated by the peak capacity. If you look at the RSDs, you see the reproducibility we get for the separation of this complex sample, which is well below the 0.1%. You see with the pressure trace that we go close to the 1500 bars of pressure that the Vanquish system offers. And you also see that the pulsation of that pressure trace is very low with the 0.4% pulsation here. And that's the feature that I meant earlier, where the low baseline noise in the detector is partially contributed by the low pulsation we have on the pump. So the flow is stable, the signal is stable, and that gives you enhanced sensitivity. If you then look at retention time precision, right? Retention time precision is not only governed by the pump. It's not how good the gradient is delivered, it's not only how good the flow is delivered or how low the pulsation is. There are other features which are of importance. And if I take these 2 chromatograms, where we show an overlay of 10 samples, you see for these 10 peaks that both these overlays look really good. There is an autosampler feature that we've enabled and that we've disabled for this experiment. But only when you look at the true RSDs in this table, you'll see that the RSDs without the pre-compression are already impressive. But as soon as we turn that feature on, the RSDs become 5 times to 1 order of magnitude better. And that means that a feature which is built in the autosampler actually helps the overall outcome. Again, it's the integrated modularity. It's how everything works together to give you the best results possible. If you look at temperature control, as I mentioned, it's one of the most complex things in chromatography that you can imagine. In traditional LC, so pressures below 400 bar, we have preheating of the solvent, we have the column thermostat in the column compartment, and there's nothing temperature-wise that happens with it. So 30 degrees solvent goes in, the column is at 30 degrees, and 30 degrees solvent comes out. And you get a separation with a plane count, in this case of 26,000. If you now go to very high pressures, if you go to UHPLC pressures, you get an effect which is called viscous heating. That means that the pressure becomes higher and higher, and that means that the friction between the mobile phase, or the solvent you're pumping through the column, and the column itself will start to generate heat from the inside of the column. If I now start to take away that heat by using a forced air mode, in this case, at the edges of the column, it means we get 2 temperature gradients. You get a gradient from the front of the column to the back due to the viscous heating, and you get a temperature gradient from the center of the column to the edges due to the thermostating method that you apply. And temperature gradients that you have in chromatography will always have a bad effect on results. You want to minimize these and control these as best as possible. And what you'll see in this case is that the plate count actually goes down. So the separation performance is less, but you do see that the peaks all move a little bit earlier. And the reason for that is that your temperature increases, so your chromatography goes faster. If you now apply the still air mode, remember we had 2 temperature control modes in our system. If you apply the still air mode, you're still going to keep that heat that is generated inside the column in the column. But rather than taking it away at the edges, you're going to keep it in the column, which means you only have a gradient, a temperature gradient, from the front of the column to the back of the column. And that means that although I don't have a uniform temperature, and the column is heating up, all the peaks move forward, I do get better chromatography because the temperature gradient that I have along the column is much more equally distributed, and that has a very positive effect on the peak shape. And then lastly, as I said, it's the system that works together to give you the best result. There's the role of data collection rate. If you remember the 14 millisecond standard deviation we had for that 69 peak overlay, and if you would plot that towards the data collection rate, as you see here on this slide, then with 20 Hertz data collection rate, which is pretty fast, but with 20 Hertz data collection rate, every data point is 50 milliseconds apart. There's no way to tell you have a 14 millisecond standard deviation if your data points are so far apart. If you go for 50 Hertz, it's 20 milliseconds, but only from 100 Hertz you start to get the points so close together that they're within this standard deviation that we've shown. And with 200 Hertz, which is the maximum of our detector, you have a 5 milliseconds distance between the data points, meaning that you get the data collection rate to be able to see the true retention time reproducibility that we can obtain on the Vanquish system. 1500 bar is an impressive amount of power and an impressive amount of pressure that you have. And it's not the only feature we have on Vanquish, but it's typically the feature where UHPLC systems are compared on. And when people ask us, well, how should I use that, we typically see 2 ways of applying this pressure. So with traditional UHPLC, let's say up to 1000 bar, you get a certain separation. And what can you do if you have the extra 500 bar that we have in our system? You can either maximize the speed, so in this case the runtime goes down from 18 minutes to 12 minutes, which is a 33% throughput increase, or you can maximize the resolution. You make your column longer, you add 2 together, or you use a different kind of column to utilize that pressure, which means you invest more runtime, but you get more peak capacity. You get a better separation in the end. And of course everything in between, because all of this depends on the sample complexity and the sample that you're analyzing. If your sample has 3 peaks, then you can still have excellent resolution, you can still have excellent speed. If your sample contains hundreds of thousands of peptides, you might want to invest more time and use a longer column and use the pressure in that way. So there's 2 examples that I can show related to biopharma. We have the highly precise peptide mapping that you see here. And this is an overlay of 13 injections. So it's not only for the samples that are well characterized, 10 peaks that we see this excellent reproducibility. Also for very complex monoclonal antibody digest with 13 overlays, there's no way to tell what the retention time reproducibility or how many runs are overlaid here on top of each other. If you look at how can you use this retention time reproducibility to your benefit, then this picture is very nice. What we've done here is we've digested, so we digested the monoclonal antibody in two different conditions. So we created some differences between the sample, although the same protein was used to create these. And if you mirror these plots, you see some differences. And if you zoom in on these, then you see that for these three regions that we've mapped out, that the peaks perfectly line up. So the retention times are actually spot on. But when there is a difference due to the different conditions we applied, you see that the peak height is changing. And what you'll see then, and how you can use it, is if you know what your standard is, and you want to check if you really made that standard, if you reproduced it, you run these two analyses on a Vanquish system, you compare the plots, and you have an idea which peaks are different, which peaks are affected, and which peaks are exactly the same. Another thing you can do with a Vanquish system is not only reversed phase analysis, and in this case it's analysis on the intact protein level, where we want to separate them based on the charges that they have. And proteins have an isoelectric point. The isoelectric point is the point at a protein where the charge, their overall charge, is neutral. So if you do an ion exchange based separation, you load your protein in its charged form. You can elute your protein in two different ways. You can either displace it by a high amount of salt, or you can change the physical charge of the protein to make sure that it dislodges from the stationary phase. And that's where pH gradients come in. What we've done with the pH gradient is we start with a low pH and we increase the pH over time, in this case from 0 to 100% B in 10 minutes, and we see where the protein elutes. The buffer system that we use is a buffer system that we have available as a ready-to-use kit. It only and it allows you to run a linear AB gradient to get a linear pH gradient as well. So it's very easy to apply, it's very easy to set up. So in this case we have a 10-minute separation from 0 to 100% B, where we have an idea where our protein elutes. And it actually is that the place at the percentage of B where the protein comes out already gives you an idea on the actual PI that this protein has. But we can speed this one up. We can zoom in on the region where the protein actually elutes. What you see, we go from 10 minutes to a 5-minute run, where we just zoom in on a portion of the gradient. And then we can accelerate that even more by zooming in on that even more on that portion of the gradient in 2.5 minutes. This is just a 3-step method development to increase your throughput, and we've brought the run time or the gradient time down from 10 minutes to effectively 2.5 minutes. With Vanquish we wanted to see how far we can push this. So what we've done with Vanquish is we have achieved gradient times and monoclonal antibody separations down to 1.5 minutes here. And to put this into perspective, let's say you need to analyze 1,000 different samples. You would have the typical 10 to 30 minute gradients. It would take you about 3 weeks to analyze all these samples. If you bring it down to these very short run times, you can get the answer overnight. And that's the throughput you can achieve. To come back, right, these were two chromatography examples, two chromatography power perspectives, so to speak, but I also mentioned there are other groups, and I want to show you this mass spectrometry example. Right? What I said with the mass spectrometry perspective is that people start with a gradient, with a separation, which is in the basis so good that extra or the missed separation, the overlapping peaks, can be resolved by the mass spectrometer. And that's exactly what this picture shows. There's a gradient done or a separation done in about 10 minutes. The runtime is 10 minutes here, and you see some of the peaks overlap. But by combining that very good basic, in the basis already very good separation, with the triple quadrupole in this case, you can make the two work together to give that answer and resolve every peak by using the separation performance and the transitions that were used for this sample. And as the last example that I want to show you this one here. This is the Stribuild combination drug assay. And what it does, it's a single tablet which has multi-active ingredients in it. And the value for the patient is quite clear. Rather than taking multiple medications during the day, he can take only one pill and has all the medication that he would need. The challenge for the customer who makes this pill, the pharmaceutical company who makes this, is that instead of having one active pharmaceutical ingredient and its impurities, now 4 active pharmaceutical ingredients and the related impurities need to be resolved. They need to be analyzed, and that's where Vanquish comes in. And the reason why I like this example so much is it combines multiple values that the Vanquish system has. It combines the performance level in terms of separation, because this run was done in less than 7 minutes, and all the actives were found. Many, if not all of the impurities were found, and there was no comparable separation publicly documented. It's on the separation aspect of performance, but it also allows you to get the quantity and the quantitation done by the sensitivity and the linearity that the Vanquish system offers. And because it's such a short run time, you can also do this with high throughput. So we've got multiple values that the Vanquish system offers combined into a single assay, and that's why this is such a nice example. That was the end of what I wanted to talk about today. Before I leave, what I want to show you is we have a dedicated hypersite on the Vanquish system. And what we have on there is we have an online virtual demo. So if you want to learn more about the Vanquish system, feel free to go to this web address, go for the online demo and explore the Vanquish system on your own. Thank you for your attention.